All right. Here we go. All right, so we are on 2.6.2. We're looking at horizontal stretch and compression. So remember before, what do we do? So again, just to kind of remind us what we've done all together, we know how to translate. We can move things up, down, left, right. Okay. We know how to stretch vertically, compress vertically. Based on our K value, we know if it's a fraction, we're going to end up with it opening up, being compressed. If it is a whole number that's greater than 1, it's going to be stretched. It's going to become long. The sides of the parabola can move towards that y-axis. It kind of gets stretched like taffy. All right, today is a little bit different. So today is horizontal stretching, which kind of looks like a vertical stretch. Or sorry, compressing looks like a vertical stretch because it pushes it in. Okay, and then we're going to have a stretch out, which is just going to pretty much, I mean, that's kind of easier to see. It's going to make it open up. Now, if I am stretching it vertically or compressing it vertically, what variable, x or y, is mainly being affected? If it's vertical, up and down is what? Which variable? Up and down? Y. Side to side, the axis kind of give us the hint on this. Side to side is the x, right? So remember, with vertical stretch and compress, we're talking about manipulating the f of x, moving up and down. The vertical axis is f of x, it's our y axis. So in that case, we just took our y, our f of x in function notation, we just multiplied it by a k. We took the entire function and multiplied the entire function by a k, we got a new function. That was our g of x, and we were graphing them, noting which one was which. So this was multiplying the entire function by k to stretch and compress vertically. And when we had f of x times 2, a whole number greater than 1, we stretch and it gets smaller. The green is when we have a fraction in there and it gets closer to the x-axis, it opens up more. Okay? What happens when the k value is negative? What's going to happen to this parabola? If it's negative, it's going to flip to face down. Just like our a value, when that's negative, right? When the a value is negative, a is out in front of the first term, then you know that it faces down. So applying a k value that's negative is going to essentially change that first function, the valence from positive to negative, if it was that way. Everyone good with what we did before? Feel like it's pretty, the components? Thumbs up, sideways down for the vertical stretch compress. Pretty good. Okay. Okay. So the video is online if you missed that day. But now we're going to look at horizontal. Okay. Now, vertical stretch compress applied to the y value. So what do you think horizontal stretch compress is going to apply to? X. X. Good. So it applies to the x value. So what I'm going to have to do is, it's going to, instead of being f of x times k, where we take the whole function and multiply by k, you're going to take k and multiply it to the x in every place that there is an x. So it's essentially saying we're going to multiply this k value to the x values. And if I look at my quick example here, x squared minus 81, you know, I'm going to change this right now, executive decision. I want you to change this to 81x. Okay? So I'm just going to redo this part then, this last part here. You know what? First up, yeah, that's fine. Okay. So look what we've done. We have our function, negative 81x here. Our k value is 3. So if I look at this, it's k times x because I'm looking for my horizontal stretch. K times x, 3 times x, 3x. Now remember, function notation reminds us what we have for x, we're going to plug it in everywhere we have an x. You see? So I had to apply the 3x to the first part that had an x. I had to apply the 3x to the second part that has an x. And if it was 20 terms, a really high order function, you would be substituting the k value into every place that has an x. The key here, this is the key. I want you to put a little key right here. Old school key. You need to put these parentheses every time. Parentheses. The reason why it's so important is you need to think about it as it's not 3 times x squared. It's 3x, that term, 3x being squared. Okay, you would get different answers if you don't use parentheses. So just use over parenthesize it. That's not a word. 3x. So 3x squared is 3x times 3x. What's that give us?
9x.
9x squared. X times x, 3 times 3. What is 81 times 3x? Negative 243 x. That's our new function. We'd call this g of x. All right. All right. You see what we're doing? You see how it's different? Okay. If it was a vertical stretch, I would have taken this function here. I would have taken this function and just multiplied the whole thing by 3. And I'd have to distribute the 3. That would be applying it to the entire f of x, the entire function. Here, we're just applying it within each x value. We're going to put it in there like that. Okay. Maybe after 1 or 2 examples, we'll have this. So what I have on the overhead over here, I'll learn how to do that later. But let's just look at right here. I want you to write this one up. I'm going to read it out. Maybe I'll just write it for it. But we can use this on Desmos. In order to create our sliders. Now remember, this came from our ax squared plus bx plus c. It's our standard form of the equation. All I'm doing is multiplying the k with the x value every place you see an x. Kx, kx. So now if we have this going on, we have our sliders, we'll be able to quickly rearrange using the sliders to find our new function. Okay. So let's try this one. Given f of x is x squared plus 2x minus 5, k is 2, complete a horizontal transformation to find g of x. So again, I want you to rewrite this as f of 2x because that's k times my x. What does f of 2x give you? Use your parentheses. Make sure you got that parenthesis action. And then check with your neighbor. Make sure they're doing well. Not just for yourself. See if they know how to do it. Oh. So set it up like that. Put your parentheses in there first. Wherever there was an x, I put parentheses. Then I know my k times x. Just throw it in there. Right? See how the parentheses helps a little bit. Maybe if you need that scaffolding. I know it's hard to see, guys. Sorry about that. Let me turn this off. Maybe I even need to turn on the overhead lights.
Don't do it.
Thank you. You saved my life. Hate those lights. All right, let's bring it back. Bring it back. Here we go. Who uses the parentheses like this? Anybody? Good. It's helpful because if it gets more complicated, you already have this process set up. So let's see. 2x times 2x. 4x squared. 2 times 2x. 4x minus 5. Who got this as our new g of x? All right, that's pretty good. Okay. So this is just like what we have in the classwork. There's no mystery on what we have to do with these problems. The next example is going to be the same, but I want you to look over here to Desmos, and let's see if we can look at it and see what these two graphs look like. That is way hard to see. Let's see how I can get this. Maybe if I could do this. No. All right, well, let's look what I set up here. I have k is 1, so I'm just trying to find the actual original function. I got a is 1. If we look at what we had there, a is 1. We got b is 2. We got c is negative 5. So this right here is set up for our original function if we look at it. Where's my vertex? Let's see. Looks like the vertex is at -1, -6. All right. So -1, -6. Now, look at this function right here. Right here. This is what we ended up with, right? Yeah. So I'm going to click on this. Actually, tell your neighbor, what do you think this is going to look like? Is it going to be more narrow? Is it going to be compressed? Or is it going to be stretched? Tell your neighbor, what do you think? All right, 5 more seconds. Here we go. That's the best I can get. All right, let's look. Raise your hand. What's your guess? What's your guess? Anybody? Yes.
Well, like compared to.
So that's hard to explain, actually. So you're saying it's going to be compressed in?
Yeah.
Okay, let's see what happens. I like that it was like this kinesthetic, like learning thing that was happening. Your learning thing was really good. All right, let's see. Here we go. 3, 2, 1. Nice. Now let's look at this closely and see what are some elements that happen. Are we at the same vertex? No. Looks like the red, our original, has the vertex here at 1, -6. And the blue vertex is at negative, those numbers. So we see a couple things happen. Instead, when we had a vertical shift, a vertical compression or stretch, right? The axis of symmetry didn't change. The vertex might have been moved up or down because it's stretched or compressed, but it was always on the axis of symmetry. Here, that doesn't happen. Here, that doesn't happen because we have a horizontal compression. What's happening actually is it's getting closer to the y-axis at the same rate. Okay? If it's getting closer to the y-axis at the same rate, then an off-centered function here. You see, if these are going in towards the y-axis, right? This one ends up going essentially halfway to it. This one's going to go halfway to it. So it's going to have the same rate of moving closer and being compressed from both sides. That moves the vertex around a little bit. Just get used to that. I want you to know, like, when the vertex doesn't line up, it's because it's a horizontal shift. That's just what's happening. Okay. Thumbs up, sideways, down for that. Kind of playing around with this so far. Okay. All right. Let's look at our second example then, and let me zoom it back out. Go ahead and start on the second example. I know you know where we're going with this, so second example right here. You're given this function, negative x squared plus 2x minus 3. K is negative a half. So there's a lot of negatives, but we can do it. Complete a horizontal translation. This was just the function I said to use to create the sliders on Edmodo. Desmos. You will need this because remember you're going to graph all these functions using Desmos and then translate them onto some graph paper. Okay, if I didn't know where to start, I would do this. Line it all out. Because whatever goes in here needs to be squared first, and then you multiply that -1 to it, because exponents come before multiplication. We'll reiterate that again. I want you to try it. We'll go over that idea again when we get it. Where's my computer? That was awesome. All right, let's see. Let's go with. And this is the key part here. When the k is negative, it reflects across the y-axis. That we're going to kind of have to keep in mind. But just remember when we were dealing with up and down, it flips it this way. This one is going to kind of turn it across the y-axis, flip it this way. All right, check with the neighbor. We're going to go at this in about 10 seconds. It's all good.
Oh, no, it's all good in the hood.
Oh, in the hood. That's important.
Yeah.
I like that movie, actually. The new one. You see?
Or, I know it's out. I haven't seen it yet.
You know what? Before I went, because my parents were busy, it was like a parent kind of like movie to go see. And I wasn't like, it wasn't exactly what I wanted to see, but I enjoyed it. Like, it's interesting to look at it. It's not just about him, it's like his interaction with these other people.
You know Mr. Brown, the engineering teacher? He wore a red cardigan yesterday, and he looked exactly like Mr. Rogers. It was uncanny.
Did he change his shoes when he came in?
I don't know. It was great. It was great.
Did everybody say?
No, I was the one who said it, and then everyone.
Yeah. Nice. All right, let's see. What are we going to put in for f of x? What are we going to put in there?
Negative 1/2 x.
Yeah, is everyone okay? I just want to put it this way to make sure that you all see it. Negative x over 2. Okay. Negative 1/2 times x, right? Negative 1/2 times x over 1 is negative x over 2. Okay? So I just want to like put it that way so it's not something, when you see that again, it's not too tricky. So let's go ahead and do negative x over 2, negative x over 2, and now we have to simplify this. So, negative x over 2 times negative x over 2, we end up with negative what? Negative x times negative x? Positive x squared over 4. We just multiply straight across. Here, this 2 and that 2 are going to cancel. So we end up with just negative x and minus 3. The final, then, our new g function is going to be negative x squared over 4 minus x minus 2. Raise your hand if you got that. Okay. All right. If you didn't, who can give me a candy crux? Where'd you go? Yeah. No.
I didn't put the negative on it, like
That.
Yeah, that.
I knew that was going to be the hardest part right here. Okay. Parentheses help us figure this out because this is real important to put the parentheses like that, just as far as the method goes, because you know you're going to change this to be your k times x. And looking here, remember, PEMDAS, we do exponent first, and then we multiply essentially the negative 1 out here. We multiply that next. PEMDAS, exponents come before multiply. Yeah? Okay. Oh, jeez. That was weird. Jeez. All right, we got our g of x. Let's see what happens. Tell your neighbor what do you think is going to happen. Oh, here you go. Tell your neighbor what do you think is going to happen when we graph the original and the new g of x in there. Don't go in front. Don't be on the video. They ask you now on YouTube if you load a video. It's like, are any children in the videos? Under 18. It's because you don't have the parents' permission to put their kid on. So I actually that never happens. It happened once when I had the kids in the class of doing the Baby Shark song. And one student who was 18, I clarified it, she's 18, she did a little dance after Baby Shark dance. That's the most important thing you learn this whole week, just so you know. Parental consent, important. Okay, here is our function to start, right here. Let's see where the vertex is for this. Oh, 1, -2. That's nice. That's nice. Okay, what is going to happen? There's two things that are going to happen. Is it, first off, going to be compressed or stretched? Stretched. Okay, I like this. Is it going to have the vertex in the same place? No. Where's the vertex going to be? What quadrant is the vertex going to be in? 1, 2, 3, or 4? 3. Tell your neighbor why the vertex is going to be on this side. Why? It's over here. You see it now? You see it now? Yeah. All right, let's see. Here we go. 3, 2, 1. Ah, very good. Very good. We have our new vertex at 2, -2. It moved from 1, -2. What do you see in common? What's in common? What's in common? The vertex has the same what? Y value. You see they're on the same line here. Lasers. Right? What did we have in common when we had a vertical stretch compression? Up and down? The vertex was on the line of symmetry, right? So in that case, the X values were in common. When we have a horizontal kind of stretch going on, we always end up with the Y values in common. Okay? So we also had a stretch. You can see it's wider than the red, our original. And it's been flip-flopped. It's been flip-flopped. We have the same y-intercept here because we basically just flipped it over to the other side. Okay? That's how these things work. And now, you are truly quadratic ninjas because, yeah, there's not a whole lot more you can do. You can rotate these things, but that's way later. So you can take any quadratic from the standard form, the parent function. You guys now know how to move it up and down, right, left. You guys can compress it and stretch it horizontally. You could stretch it and compress it vertically. You can flip it this way. Honestly, you can make any quadratic because you know these different things. There's no quadratic you can't make now. Okay? So that's a good accomplishment. Someone taught you well. All right. Who thought of something funny to say at the end of class?
We should all do Erica's laugh.
Erica, can you demonstrate it? No?
That's like Skip Nelson from The Simpsons where he goes,
Should we do a ha-ha on 3? Ha-ha. Do that? On 3? Nobody says yes. You guys want to do that on 3? Yeah? All right. Ha-ha on 3. 1, 2, 3. That's good enough. All right. Thanks for watching.